natural log. All right, so exciting times. Well, we could do the limit definition. We'd hit a roadblock almost immediately. Okay, so definitely not the way to go. You'll take my word for that, because all I would end up doing is showing you me plugging in x plus h for this, writing it in the difference quotient, and then saying, okay, now we're stuck. We can't do anything with that, so let's try something else. All right, so I kind of just bypass all that. Let me write this as y equals ln of x for simplicity's sake. All right, I don't know anything about the derivative of a natural log, but I do know how to find the derivative of an exponential function. And we can convert from log to exponential form, yeah? So x would be equal to e to the y. All right. So normally I'd be taking the derivative of a function of y in terms of x. That derivative would be noted as dy dx. Well, now it's a function of x in terms of y. So my notation should change accordingly. So dx dy. Independent variable is now y with the dependent variable being x. What is the derivative of e to the y? E to the y. All right. Okay. Well, I don't want dx dy. Let me put that over a 1. Because, yeah, I don't want a dx dy, so let's make it a dy dx. I can't just flip one side, so let's flip the other side. Also, legal maneuver is basically a shortcut to cross multiplication. You can flip one side of a proportion as long as you flip the other side. You can swap diagonals any way you want. All right, that's all a result of the idea that you can cross multiply. By being able to cross multiply, it allows you to do all that stuff too. All right, so I need a derivative in terms of x, and that clearly has a y in it, so that's a problem, but an easy fix. Because e to the y is the same as what? X. Because it says that right here. E to the y is x. All right, so anywhere I have an e to the y, I can replace it with an x. So what we just got from this is, and actually much easier, I think, than using a limit definition, is that the derivative of the natural log of x is just a 1 over x. But the chain rule component of that has to allow for the fact that maybe it's not just an x that we have the log of. We have a log of a sine of x, log of anything of x, all right? But don't get confused by the fact that maybe sometimes it's just the log of 4, like on the previous page. If it's log of 4, it's not a function of x. So when we take the derivative, we're taking the derivative of a constant, it goes to 0. No rules need to apply other than the derivative of a constant, right? So we get our chain rule variation on this, which tells us that if we have the natural log of a function, that we would do 1 over the function, just like we would do 1 over x, but then we also have to multiply by the derivative of the inner function itself. All right. So natural logs, not too bad when you look at it from that perspective. Number 1 as a constant multiple. So 4 times 1 over x. Number 2, power rule, 2x, plus, well, natural log is just 1 over x. Number 3 gets a little juicier because we got a little bit of chain rule going on here, but nothing too crazy. So it's power rule followed by the derivative of the inner function. So f prime of x would be equal to, so something to the third becomes 3 times the something to the second power. And then we multiply by the derivative of the something. So 8x becomes 8. 3 ln of x becomes what? 3 over x. All right. So I mentioned before, don't forget that pre-calc is a thing. That's going to come up in number 4. It might have come up in number 3. I mean, I gave it some consideration, at least in my mind. It's like, sometimes I will look at it and say, is there any value to actually multiplying this out before I get started? Will it make my life easier? No? Okay, chain rule it is. Okay. If it is, I mean, if something will cancel away nicely, then yeah, go for it. But sometimes it doesn't. Sometimes you just gotta crack the old knuckles and get into it, you know? And then while you're at, elbows, knees, and neck, and toes, and when you're 40, you'll have arthritis. But you'll be good at math. So in the end, yeah, it's a good trade-off. Agonizing pain, but really solid understanding of math. So the pre-calc part of this, I could use some chain rule. I could do the 1 over u times u dx. But the natural log of a product, because we have product rule for derivatives, but we also have a product rule for logs. ln of 5 plus ln of x. The derivative of which would be just, well, ln of 5 is constant, right? So that goes away. ln of x is the only thing that's relevant, so 1 over x. Honestly, I only needed to do that once before. I was like, okay, so what you're telling me here is it doesn't matter if there's a coefficient of x. A numerical coefficient, it's still going to be 1 over x? Cool, got it. Right? And even if you use the u rule, it would be 1 over 5x times 5. The 5s are going to cancel anyway. All right? So when you get to something like this, it just became a whole lot easier. Because now we're looking at product rule, sure, but product rule where I already know what the derivative of the natural log component would be. So my first function, 3x squared, times the derivative of the second, 1 over x, plus the second function, ln of 4x, times the derivative of the first, which would be 6x.
Where is that rule?
Which rule?
How do you know to add this?
Product rule. First times the derivative. Yeah. All right. Number 6 is kind of a trick question. Because a log exponent rule makes you think you could just hop it over. Because if it was just the x being raised to the power, then that'd be exactly what you do. But here it's chain rule. So 4 ln of x to the third times 1 over x. Because it could be a matter of just looking at where y4 crosses the x-axis. I mean, if that's the case, then it's a pretty easy question. But here, maybe a little bit more involved if we're assuming that we have to do it analytically. So f prime of x, well, we get a product of two functions. So my first function, x squared, multiplied by the derivative of the second function, 1 over x, plus the second function, 1 over x, times the derivative of the first, which is 2x. All right. Previous questions, it was hit or miss as to whether or not you needed to simplify, and that's because either the directions didn't tell you to, or there was no need to, just based on the nature of the question. It was just find the derivative. Here we actually have to do something with it. So it benefits us to take it upon ourselves to simplify. So x plus 2x times the natural log of x would be the simplified form of my derivative. Horizontal tangent, that happens when the slope of the tangent line is equal to 0. The derivative is the same as the slope of the tangent line, So set this puppy equal to 0. On the right-hand side, I have a common factor of x. I don't think it was that funny. Sympathy chuckle, I appreciate it. All right, so we have two factors. Each one of these factors could be equal to 0 technically, but it doesn't always play out that way. So set them both equal to 0 and solve. And then analyze. So x equals 0, 1 plus 2 ln of x equals 0. I'm going to toss the x equals 0, and that's because it's outside of the domain, not in domain. If you look at the original function, it's x squared times the natural log of x. If I try to put a 0 into a natural log function, can't take the natural log of 0, can't take the natural log of a negative number, so that's out. All right? So where we might have wanted to toss the other one and keep the 0, turns out we have to toss the 0 and keep the other one. So subtract the 1, divide by 2, we have ln of x equals negative 1/2. Solve for x, convert it into exponential form. You have x equals e to the negative 1/2 power, which is a number. Right? So, I mean, you don't actually have to determine what that leads to in the original function. It didn't ask us for a coordinate. It says for what values. I'll take it as a typo, parentheses around the s to indicate that it's not necessarily more than one value. Yeah, so for what value or values of x. So once I get x, x marks the spot. But you should give it a quick look and make sure that it is something that will exist within the original function. Right? Because if it's like the 0 and it doesn't exist at all, then there would be no solution. All right? So if I plug in an e to the negative 1/2 for x, that's not a problem. Polynomial functions are forever continuous and differentiable. And this is a real number. It's not the nicest looking number, but if I put that in my calculator, if I'm allowed to use a calculator, I would get some number. It would be a decimal, but it would be a number. If I take that number and plug it in here, it's actually even more convenient because I have that power rule for logs to work out. Ln of e to the negative 1/2 just becomes negative 1/2. Right? So it works out with only this x value, this particular x value. And so that would be our solution. That is the only value of x that has a horizontal tangent. Now, can you pull out that particular solution in that particular form from the calculator? I don't know, probably not. You're going to come up with, like, just visually or based off of an analysis of a decimal. You see a nasty looking decimal and you say, oh, clearly that's 1 over the square root of e. Obviously. No doubt in my mind. I mean, when you see 6.28, you're like, all right, that's probably 2 pi. But when you see point something, 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 you're not looking at that and saying 1 over the square root of e. Okay, so even on a calculator part of an assessment, depending on how the question is organized, you may need to, some analytic work anyway. Okay? But, it's kind of question that a little harder than it might seem initially. Definitely fun, though. Page 55, number 7. Just got to remember that for later. So when I upload it, I can call it the right thing.